This video is about multiplying rational expressions, but before we actually talk about that, I want to quickly just review multiplying fractions in general. If we are, say, taking 8 over 15 times 25 over 28, there's a couple different ways that you could look at going about this problem. If you're multiplying fractions, you don't have to get a common denominator. All you're doing is you are multiplying the two numerators and multiplying the two denominators. Basically, everything's going on at the same point in time because fraction bars, as we know, is division, right? Fraction bars mean division. And if we're multiplying, well, multiplication and division are the same step in order of operations, so there's not a whole lot of special stuff going on here, really. So if you take 8 times 25, you would get 200, right? Which maybe you know off the top of your head, maybe you have to grab a calculator. With 15 times 28, I would imagine a fair amount of you would probably want to use a calculator for that, but it's going to give you 420. Even after doing those two things, even if you could do both of those two things in your head, you're still going to have to simplify this fraction. So if you don't have a calculator for this, then you have to say, okay, I know 200 and 420, well, they can both divide by 10, certainly, because they each have a 0 there, right? So if I divide them both by 10, then it's 20 over 42. And maybe you can say, well, we can see it can divide by 2, so if I divide both of these by 2, then I've got 10 over 21. And then you have to question to yourself, is that really the simplest version? Is it true that none of them, nothing can divide with both 10 and 21? All that sort of thing. Another way you could go about doing this problem, instead of doing everything we just did there, we could take each of these numerators and each of these denominators, meaning the 8, the 25, the 15, and the 28, and we could break all of them down separately to their prime factors. For example, 8. If we were to break down 8, that breaks down to 2 and 4. 4 breaks down to 2 and 2, meaning we could write this in its prime factorization as 2 times 2 times 2. Likewise, 15, if we break that down, well, 15 breaks down into 3 and 5. 25 breaks into 5 times 5. And 28, you could say break it into 4 and 7. I mean, you have some options there, but 4 and 7 would be one of the options. And then 2 and 2, you could have gone 2 and 14. Either way, however you break it down, eventually you will get prime factors of 2 times 2 times 7, right? That's what we're looking at right now. If we are multiplying these two fractions, and we already said that fraction bars are the same thing as division, well, what's anything divided by itself? 1. I mean, effectively it cancels out, right? So for example here, I see that I have a 2 in my numerator that I could cancel out with one of the 2's in the denominator, right? 2 divided by 2 is 1. They just cancel out. Or you can write the ones if you want to. I also have another pair of 2's. I have a 2 on top and a 2 on bottom in my numerator and denominator that could cancel out, which would just be 1. I also see that I could take 5 divided by 5 to cancel out to just 1. And so now that I've done all of that and taken out all the pairs that I could match up, well, I have just a single 2 and a single 5 in my numerator. 2 times 5 is 10. I have a single 3 and a single 7 in my denominator. 3 times 7 is 21. So you see, we get the same answer of 10 over 21, but now I don't have to even wonder if I've reduced as far as I can. And I would argue that that is a lot less work if you don't have a calculator, because doing 15 times 28 without a calculator would take a little bit more than likely. Either way, what we just did here is basically the concept we're going to use for when we multiply with rational expressions, because you definitely can't use a calculator on those, because rational expressions means we've added variables, we've added the alphabet into math, right? And so you're not going to be able to use your calculator, which means we are going to want to factor each piece separately and then see what we can cancel. Let's take a look at this example. We are multiplying two fractions together, so we don't have to worry about flipping the second fraction or anything like that that you need to do if you were dividing with fractions. This is just straight multiplication.
What we want to do is we want to see what we could possibly simplify this into. And so we want to take each part of this, meaning each numerator and each denominator, and almost right now we want to look at them as four separate problems basically. We want to try and factor each of these pieces as far as we possibly can. Then, after we have factored all of them as far as we can, we'll put them all back together in one big expression and see if we have things that can cancel. Specifically between the numerator and the denominator, right? Because fraction bar is the same thing as division, so if we can find anything that matches between the numerator and the denominator, we could just cancel it out, making our problem much easier. Let's start with our first numerator, top left of our problem you could say. We've got x squared plus x minus 6. If we are looking to factor that, the first thing we should always look for is a greatest common factor, a GCF. I do not see one here, so moving past that, we want to look for another way to factor it. As you guys know, if you've already watched my factoring video on here, I like to do it by what I call the x method. So we take our a value, the coefficient in front of x squared of 1, and our c value, the constant term, and we take a times c, 1 times negative 6. Then we take our b value, the coefficient in front of just the x term, of 1, and we are looking for two numbers that multiply to negative 6 but add to positive 1. In this case, 3 times negative 2 is negative 6. 3 minus 2 is 1. So we could factor this to x plus 3 and x minus 2. If we take a look at our first denominator of 2x squared, that's just one term. I don't really see a whole lot of factoring we can do there. I guess if you wanted to, you could split it up into x times x instead of x squared, but you don't necessarily need to do that. You could just leave it as 2x squared as well, whatever you prefer. Looking at our second numerator then, the 2x plus 8, that one does have a GCF, specifically of 2. So if we pull 2 out, we are left with x plus 4. I do not believe x plus 4 is something we can factor further, so I think we're done with that as well. Finally, we have our second denominator of x squared plus 7x plus 12. I don't see a GCF for that one, so we'll try to x method this the same way we did our first numerator. 1 times 12 is 12. B value of 7, so we need two numbers that multiply to 12 but add to 7. 3 times 4 is 12. 3 plus 4 is 7. So we can have factors here of x plus 3 and x plus 4. Now that we write this in their factored forms, we can see we do have some things in common. I see an x plus 3 that matches between the numerator and denominator, so x plus 3 divided by x plus 3 is just 1, meaning they're effectively canceled. I also see an x plus 4 over an x plus 4, which is just 1. Those can cancel. I also see a 2, a standalone 2 that's away from anything, right? Not this x minus 2. This 2 is bound with the x and we can't mess with that. But this 2 is standalone, and this 2 is effectively standalone since it's just being multiplied to the x squared, not added or subtracted. And so these can cancel as well. Remember, it is important to recognize that multiplication is something that you can split things up with because we're trying to cancel through division. If we're trying to cancel through division, then multiplication is not going to hinder us because multiplication and division are the same steps in order of operations. But addition and subtraction are their own step. So when you have this x minus 2, the x and the 2 are bound to each other because of that subtraction. You can't cancel one out without the other going as well. So because of that, we have to leave it as x minus 2 in our numerator, and then we are also left with an x squared in the denominator. And that would be your final answer after simplifying.